now, we've been focusing on the interior gateway protocols that we are going to run inside our corporations. Now we're going to talk about exterior gateway protocols that we're going to run between organizations. And I used plural there, but I shouldn't have. We're not going to talk about more than one exterior gateway protocol. We're going to talk about the star of the show, the only one that we use today, Border Gateway Protocol BGP version 4. This is indeed standards-based, and it's our only example of an exterior gateway protocol. By the way, historically, there was a predecessor to BGP, and it was named EGP. But this is no longer used today, so we're going to standardize on the use of Border Gateway Protocol. This is going to be used to route between autonomous systems, not within an autonomous system, but instead between autonomous systems. BGP is what we said before, a path vector routing protocol. For a metric, it's going to use a whole series of attributes that we can tune and control in order to affect which path through the autonomous systems data is taking. It's really like a policy-based routing approach, and policy routing is very important when it comes to internet service providers routing traffic between each other for different autonomous systems. BGP has no class. Yeah, that's right. BGP is classless. It does indeed send subnet mask information, as you might guess. Therefore, VLSM and what we call in BGP aggregation are both possible. Scalable? Is it scalable, you ask? It is the most scalable of all of the routing protocols that we have discussed. As a matter of fact, currently the global internet BGP table is around 300,000 different routes. Wow. So you talk about scalability, this is the ultimate scalability for routing protocols. How about stability? Yeah, it is indeed very stable. This is because there's no real ever solid convergence of the internet routing table. As you might guess, when there is like 300,000 routes involved, something is always changing. And BGP is designed to enter stability into this overall process. Remember, with BGP, it's all about the enforcement of policy. So it doesn't just use one simple metric value that might be tied to something like bandwidth. Instead, BGP has a bunch of different attributes that can be manipulated in order to enact particular routing policy. BGP is used in two particular scenarios, really. When we're a service provider and we want to provide transit to other destinations on, like, the public internet. Absolutely. Service providers are going to run BGP in order to provide transit for internet traffic. But what about non-ISPs that are using Border Gateway Protocol? Now, we might have a big enterprise that does a lot of internet traffic, and it has connections to 2 or more internet service providers. This is what we call a multi-homed network. When you have these big important connections to more than one internet service provider, you are organized in what's called a multi-homed design. And if you're a big enough enterprise, you probably want to control very carefully. You want to control how traffic goes in and out to these multiple internet service providers. So Either you are an internet service provider yourself, like ISP1 in this diagram, and you are taking in traffic from multiple customers, and you have to move that traffic on to different internet service providers. So you are doing BGP as one of these transit networks, or maybe you're a really, really big enterprise with sophisticated connectivity requirements out to multiple different internet service providers. In this case, you might be utilizing BGP in order to optimize the flows of traffic out from your different internet service providers. Remember, we refer to this capability as multi-homed. Okay? We are multi-homed out to different ISPs. So most of us don't need BGP. Yeah, that's right. Most of our networks don't need it. That's another reason I think students sometimes struggle with BGP. They come into courses in Cisco networking with little to no BGP experience. They have little or no BGP experience because the extent of their networking real life practice comes with the plethora of networks that don't need BGP. Maybe we have single internet service provider connectivity, and in this very simple single ISP connectivity configuration, all we need is default routing. All we need to say is, okay, look, if we don't know internally how to get to a particular destination, we're going to go ahead and rely upon our single ISP to take care of that routing for us. So we use a default route pointing to our single, simple internet service provider configuration. Maybe we have limited memory or limited CPU resources. So maybe we'd love to run BGP, but maybe we just simply don't have the horsepower to do it. By the way, we also wouldn't use BGP if we don't own the IPv4 address space we are utilizing. Okay, so oftentimes we're just going to go ahead and get our public address from DHCP, from our service provider, and they're taking care of the advertisement of that public address for us. Right? We don't own that public address. Many times, the most common small office, home office environment, for example, the real publicly routable IP address that's on the internet router for the small office, home office, nobody owns that in the small office, home office. They're renting that number, and that number could change. Certainly could change based on the internet service provider. By the way, I've described my small office, home office to you a couple of different times appropriate in this course. And as you might guess, I do own the public address space that my small office, home office has. So I could potentially be a candidate for BGP, but I don't, because I don't have any special needs when it comes to using my primary and redundant ISPs. So even though I own my own IPv4 address space, I don't need to get involved with BGP because I don't have any complex in and out of the internet requirements. Similar to EIGRP, OSPF, ISIS, BGP uses a three-table structure. Interesting. It follows the design guidelines of those protocols. It has a neighbor table, and it makes adjacency with what it calls peers. It has a topology table, known as simply the BGP table, and this is a list of all possible prefixes. And then from this table, it tucks best routes into the routing table. Very, very similar to our discussion of EIGRP. Very, very similar. With BGP, the devices are going to make their peerings or adjacencies or neighborships, however you want to call it. The official terminology that BGP uses, by the way, is indeed peerings. So the BGP devices establish their peerings. They then start exchanging updates, and they then start creating these best paths for routing information. Pretty darn cool. With BGP peerings, there are indeed different types of peerings that are created. When we create a BGP peering with a neighbor that is outside of our autonomous system, this is called an IEBGP peering, an exterior border gateway protocol peering. When we create a peering with devices inside our autonomous system, we create an iBGP peering. It's important to realize your different peerings, your eBGP peerings and your iBGP peerings, because the rules change. The rules change as you have different types of peerings. Let me go ahead and demonstrate this so you know exactly what I'm trying to say here. So let's say we have this BGP infrastructure and we have this autonomous system number 100. So this is BGP AS 100. And inside this BGP AS, we have this device which peers with this device which peers with another device. Then this other device peers with another autonomous system. This is AS 200. In this AS, we have this device peering with this device. Okay, so the peerings that are inside the autonomous system, these are called our iBGP peerings. And this peering between autonomous systems is called our eBGP. So we've got our internal BGP peerings, we've got our external BGP. Now, what happens here is the rules change for iBGP interactions versus eBGP interactions. Let me give you two famous examples. The eBGP peers are assumed to be directly connected. So our assumption is with eBGP peerings that they are direct connections. If they're not, you have to go in with a special command called iBGP Multihomed, and you have to train the devices that they're not directly connected. Otherwise, the devices will not function with BGP. Yikes. So the BGP is not going to work in an eBGP scenario where there's no direct connectivity. This assumption and this modification has no equivalent in the iBGP. In the iBGP peerings, there is no requirement for direct connectivity. Now, something else to point out that would be interesting about the iBGP situation. When an update, let's say this router down here has a prefix that it wants to share. I'm pointing to the router in the lower right corner in AS 200. When it creates, or it has a prefix that it wants to share, it's going to have no problem sending it to its neighbor utilizing iBGP. And then via eBGP, it's going to go over to this router. And then this router is going to send it to this router via iBGP. But then, let me grab a different color here. Then we're going to have a real problem. It won't go from this router, I'll number this router 1, to this router number 2. It will not go by default from 1 to 2. Why won't the prefix go from 1 to 2? Well, there's a special rule in iBGP called the iBGP split horizon rule. There we have that term split horizon again. The iBGP split horizon rule says that an update learned from iBGP, this update right here, will not be sent to other iBGP. The iBGP split horizon rule says if we learn of an update via iBGP, we won't send it to other iBGP peers. It turns out in BGP there are 3 possible solutions to this. we can go ahead and connect everything via a full mesh of iBGP peerings. Or we can go ahead and use something called a route reflector. Or we can organize our devices into what are called BGP confederations. So there are solutions to the iBGP split horizon rule. By the way, that is a loop prevention mechanism, by the way. And three options: full mesh, utilize something called a route reflector, or utilize BGP confederations. So notice iBGP peerings versus eBGP peerings. This is an important concept because eBGP peerings have their own thing to worry about, like direct connectivity, and iBGP peerings have their own unique set of issues to worry about, like the fact that there's this iBGP split horizon rule. So with iBGP peerings, we have the neighbors in the same AS. They don't need to be directly connected, and they feature the iBGP split horizon rule as a loop prevention mechanism. As a result of the iBGP split horizon rule, we might need to full mesh our peerings. But by the way, we know anytime we have the full mesh rule, we get into that situation where, oh boy, we are going to be creating a lot of different peerings. That formula of that n times n minus 1 divided by 2. So, as you might guess, one of the most frequent solutions is not to engage in full mesh. Instead, we often utilize a route reflector in the BGP environment to fix this problem, or we go ahead and use something called BGP confederations. By the way, if you do the math on your formula for full mesh, it gets real crazy real fast, doesn't it? 1,000 routers in the BGP AS would mean you'd have nearly 500,000 peerings you would have to create. I guess that's good if we're getting paid by the hour, but it's really bad if we're a salaried employee, isn't it? By the way, route reflectors, great solution here. Confederation, great solution. Route reflectors, they are just going to literally take the iBGP update and they're going to reflect it out to devices that are configured as route reflector clients. Nice little, easy to implement, easy to design solution for this iBGP split horizon rule. And BGP confederations, they're a little more complex, but what you're doing with BGP confederation is you're just creating sub-autonomous systems within the overall main autonomous system. This gives you eBGP-like behaviors. Let's take a look. Instead of going and doing some full mesh between all of these routers, which would be a nightmare, the designer here went ahead and took the main AS of AS100 and he organized it, he or she, into sub-autonomous systems. And these sub-autonomous systems, even though they're technically in the same AS, they will have this eBGP-like behavior between the sub-autonomous systems. So those double-headed arrows I drew right there, these are our eBGP-like relationships. So confederations are cool ways to eliminate the number of iBGP peerings you have with these sub-autonomous systems by implementing these sub-ASs, which will cause eBGP-like behaviors between the sub-ASs. Please notice that in these scenarios, you might also be utilizing route reflection. You might also use route reflection in the sub-autonomous system. So you can use a combination of designs. You can use confederation and you can utilize the concept of the route reflector. In fact, looking at this design, I can see that's what we're going to have to do up in sub AS 65001. Because look at this. If an update comes in here via iBGP, it's not going to flow over to this router via iBGP. Uh-oh. So we can go ahead and make this device a route reflector, and that's combining two design approaches, isn't it? We have a confederation approach here to configuration. Inside that confederation approach, we also are using the route reflector design solution. Now, early on in this lesson, I told you about BGP's interesting use of these path vectors. Well, I'm sure you want some examples. Well, one path vector attribute that's got to be there for sure is called next hop. Obviously, with each BGP prefix, there has to be some indication of where the traffic should be sent to get to that particular destination. Then another path attribute that's very interesting is the AS path attribute. This lists all of the autonomous systems that the prefix has passed through in its journey to get to you. It's kind of like a hop count, only it gives us a lot more detail. It tells us specifically what autonomous systems have been traversed as that update makes its way to us. How cool. Something else that happens is the origin attribute. The origin attribute tells us how the prefix got into the BGP system to begin with. For example, did it come in via the network command? And the network command is how you go to a router and you tell it to advertise a particular prefix. Or did the prefix protocol the redistribution approach? There's some more attributes that are attached to prefixes like local preference. This is so that you can influence the way traffic comes into your autonomous system. Or the MED attribute, called the multi-exit discriminator, that will allow you to easily influence how traffic leaves your autonomous system. There's the aggregate and the aggregator. These are for summarization in BGP. So these are just some of the path vector attributes that service providers can tweak and tune in order to enact policy when they are influenced. There's so many attributes, by the way, that they literally design categories for the attributes. For instance, if you're a well-known attribute, all BGP implementers, all BGP designers, all BGP vendors of equipment have to support that attribute. If you're an optional attribute, well, then a particular BGP equipment vendor doesn't have to. Mandatory and discretionary, these indicate whether the attributes must be present or don't have to be present in updates. And finally, a categorization of attributes is transitive versus non-transitive, meaning will it pass between neighbors or will it not pass between neighbors? BGP systems will analyze all of these attributes and then determine the best path to get to a destination. This is a very complex decision process, And you can find it. You can find it just with a simple Google search. Okay? If we search Google for Cisco BGP Bestpath Selection, for example, I pull this up so you can see it. If you do a Google search for Cisco BGP Bestpath Selection, you'll get the BGP Bestpath Selection algorithm. And sure enough, you can walk through the complex set of steps that are used to arrive at a best path. Notice there's a few rules that would cause the router to ignore the path. Like, for instance, if there is no next hop accessible. Yeah, that would cause the path to be ignored. Then once the path isn't ignored, then BGP will work through a sequence of steps in order to decide what is the best path to get to a particular place. It's very complicated. It involves a lot of different steps, and this is because of the complex nature of BGP and policy-based routing determinations. Well, that is our look at BGP. Again, complex, a lot going on there, and it may be something that you want to review several times in order to make sure you've got these design factors for BGP memorized for CCDA certification. By way of exam review, we ask, what are two types of peerings? What are these two types of peerings? And give us a little description of each. Well, that's real easy for us, isn't it? We know that there are two types of peerings in BGP. There are the external BGP peerings. Okay, so we have external BGP peerings, and these external BGP peerings occur between autonomous systems. And then we know there are internal BGP peerings, and these happen within our autonomous systems. These different types of BGP peerings are important because we know there are different types of issues that arise. For instance, with iBGP peerings, we're assuming our direct connectivity. With iBGP peerings, we have this very important concept of loop prevention called the iBGP split horizon rule, and that's going to cause us to design either full mesh, route reflected, or confederated solutions. Well, we are about to turn a major corner in this course. For those of you that are like, oh, Anthony, my goodness, enough about routing protocols already. Well, good news for you. We are indeed going to round a corner here, and we're going to, in our next module of the course, module 6, we're going to go ahead and focus on something that's very interesting to me. I hope you find it interesting as well. We're going to focus on security, designing the security services of a modern network.